My name is Jale, a research associate from Imperial College London. This video presents our work titled A Static Modeling and Evaluation Framework for Soft Robots with Reinforced Chambers. This is a collaboration between Imperial College, UCL, CMU, and CSIRO. Soft manipulators with fiber-reinforced chambers are suitable for tasks requiring consistent and large motions. There are mainly three designs described in past literature: the unreinforced, body-reinforced, and chamber-reinforced structures. Chamber-reinforced designs generally offer higher bending consistency, a larger bending curvature, and better preservation of internal working channels. Currently, most researchers rely on trial and error prototyping, which is time-consuming and not systematic. So our motivation was to build a framework that allows designers to evaluate robot geometry, materials, and their performances before the robot fabrication. The top left video demonstrates a chamber-reinforced soft manipulator with very dexterous motions. Our contribution is a complete modeling and evaluation pipeline for these fiber-reinforced chambered manipulators. Specifically, we provide first a static modeling framework that predicts both the forward kinematics and the tip force generation. Secondly, a design evaluation workflow integrating cross-sectional geometry, hyperelastic materials, as shown on the right-hand diagram. Thirdly, a user-accessible GUI toolbox enabling designers to test ideas before making physical prototypes. This framework allowed informed decision-making during early-stage design. Our analytical modeling framework is based on the static crossroad, while incorporating several hyperelastic material models. We first established the forward kinematics model, and by imposing a position constraint at the tip and considering chamber lengths, we then compute the corresponding tip force in the bending plane. To make the modeling framework accessible and user-friendly, we developed a standalone GUI toolbox. Here, users can customize cross-sectional geometries of the robot and set various material models as highlighted in Area 1. Area 2 further plots the corresponding stress-strain curve of the selected material model. To simulate robot kinematics in the free space, solver settings and applied actuation pressures are in Area 3. External tip force moment can then be applied to the robot, and resulting loaded kinematics results are displayed in Area 4. Finally, setting and results of tip force generation is highlighted in Area 5. The GUI enables rapid design iteration. In practice, users can examine various designs in minutes before any modeling or casting. The GUI toolbox is accessible upon request by scanning the QR code. Robot dimensions and material parameters need to be set first. These settings can be displayed in the GUI. The next step is to set the actuation pressure and settings for the solver, such as numerical tolerance and optimization algorithm. The result can be displayed directly. Building on above parameters, the force can also be simulated in the GUI. Details of the instruction of the toolbox can be found in our paper. To validate the forward kinematics and tip force generation models, and further to evaluate robot's performance, we built a dedicated benchmark system. It includes a kinematic tracking setup using Aurora or other cameras, a force measurement rig to characterize the robot's tip force. The platform accommodates manipulators of different lengths and diameters. In combination of the analytical modeling framework, the complete modeling and evaluation framework of soft manipulators is achieved. Two fabrication paradigms are summarized to manufacture soft robots with different dimensions. Specifically, method 1 is more suitable for fabricating large-scale robots. For instance, the diameter is equal or larger than 15 mm, while method 2 is more applicable for soft robots with diameter smaller than 15 mm. Main difference of two methods lies in the modes of the actuation chambers. Method 1 and Method 2 both comprise a four-step fabrication procedure. In this work, 8 types of robots were fabricated and evaluated, with different diameters and different lengths. This table summarizes the dimension details of different robots. Specifically, robot diameters are between 10 mm and 25 mm, with two lengths of 40 mm and 60 mm. The robot is fabricated using EcoFlex 50, and the stress stretch curve is reported. Results of bending angle prediction for a robot with 25 mm diameter, 60 mm length is reported on the right-hand side. Results highlight that the chamber stiffening effect is generally less obvious when the pressure is low, for instance less than 0.5 bar. In contrast, the simulation diverges from the experiment under a high pressurization level, for instance larger than 1 bar. These results highlighted that considering the chamber stiffening can improve modeling accuracy and large deformation. Next, we look at full workspace prediction for 8 types of robot. Results on the left-hand side show that for most manipulators, the median position error is less than 5 mm for shorter robots and under 10 mm for longer robots. Additionally, the selected hyperelastic models perform similar. All of them outperforms the linearized material model. The important point is that the modeling framework consistently and reliably predicts the overall reachable workspace of chamber-reinforced manipulators. We then evaluate how well the model predicts tip forces. We run blocked force measurement with the actuation pressure up to 1.5 bar. The experimental setup is shown on the left-hand side. Prediction accuracy is strong, as shown in the table, with average percentage errors around 3% to 6% depending on robot size. Please note that for 10 mm robots, the error increases as the resolution of the force sensor is about 10 mN, which is about 10% of the maximum achievable tip force. In summary, across different material models, force predictions remain consistent and stable. This demonstrates that the model is not only useful for kinematics, but also for manipulation tasks where force output matters. To demonstrate the application of the proposed modeling and evaluation framework, we present a laparoscopic soft manipulator design. The design constraints for this minimally invasive surgery include an outer diameter under 12 mm to fit the commercially available trocar port, a working lumen for camera or other props, a desired bending angle of over 100 degrees, and finally, a moderate tip force between 0.3 and 1 Newton. Using the GUI, we can search over design options instantly instead of fabricating many prototypes. The working flow is shown in this slide. In the simulation, 3, 6, and 9 chambers are explored. Meanwhile, different silicon materials are tested. Results demonstrate that softer materials generally cannot achieve sufficient tip forces. For instance, when the robot is fabricated using the EcoFlex 50, the maximum tip forces is 0.16 when the actuation pressure is 1.2 bar. One promising design identified by the simulation results is when the robot is fabricated using dragskin 10 with 9 chambers. In this case, the robot has an overall diameter of 11.4 and a central working channel of 3.6. When the actuation pressure is 3 bar, the bending angle is around 106 degrees and the tip force is around 0.38. This configuration fits the surgical constraints well. When then fabricated, the manipulator directly from these dimensions and using the proposed fabrication paradigm. The evaluation platform is then used to characterize the performance of the fabricated robot. Results show that the maximum bending angles achieved are 150 degrees and 170 degrees for the and two pair actuations respectively. The corresponding average modeling errors are 4 degrees and 5.6 degrees. Additionally, footage on the right-hand side shows the tip forces with maximum measured and simulated values of 0.34 and 0.38 Newton. The model's error in force prediction is about 5%. In a plastic human phantom, the designed software manipulator works together with a vertical grasper. The robot is actuated by the benchmark platform presented before. To conclude, we introduced a general static modeling and evaluation framework for soft manipulators with reinforced chambers. The framework predicts both forward kinematics and tip forces, capturing key behaviors such as fiber reinforcement and chamber stiffening. We also provide an intuitive GUI toolbox that allows designers to explore robot geometries, materials, and behaviors without fabrication. And our case study demonstrates how the toolbox can directly support real application-driven design. Thank you for watching this presentation. If you have questions or would like to try the toolbox by yourself, please feel free to reach out.